One kind of equation that shows up from time to time where a substitution can be helpful is a so-called homogeneous differential equation. So a homogeneous differential equation, first order equation, dy dx, if your equation looks like dy dx equals f of xy, so some combination of x's and y's, if this right-hand side function f satisfies this equation, so if you plug in, if you replace x with t times x and y with t times y, and then you simplify this function and it actually is the same as it used to be, then it's called homogeneous. Then this differential equation is called homogeneous. What this is really getting at is that all the terms in f have the same total power of x's and y's. Okay, that's sort of the spirit of what a homogeneous differential equation is going to look like. But you know, for it really to count as homogeneous, it has to satisfy this equation with f. Experience shows, so somehow someone stumbled upon this idea for a substitution someday, long ago, probably in the 18th century, that if you have a homogeneous differential equation, this substitution, either taking y to be u times x or x to be u times y, turns what may be a hard-to-solve equation into a doable equation. So just for an example, let's try solving this differential equation. Now, it's not clear that this is a homogeneous equation, so let's try to make it look like this to see if it is homogeneous. So first thing we're going to have to do is move the left-hand side to the right. So then we get x dy equals minus x plus y dx. And then we can divide both sides by dx and by x, like so. So our dx's simplify away on the right-hand side. On the left-hand side, the x's simplify. And we get dy dx equals minus x plus y over x. Okay, so is this actually a homogeneous equation? Well, if you look at this sort of idea of what homogeneous is, all the terms in the right-hand side have the same power of x and y. Yeah, that's true. They all have a total power 1, right? The x is power 1, y is power 1, and this x down here is also power 1. And, you know, checking the official definition of what it means to be a homogeneous equation, right? The function that is our right-hand side is f of xy is minus x plus y over x. So what we need to check is what happens when we replace x with t times x and y with t times y. So we get minus tx plus ty over tx. And then if you simplify this, well, all the t's just simplify away. And so this is the same as f of xy. So this differential equation is homogeneous. So let's do the substitution y equals u times x. So u is, remember secretly, it's an unknown function of x. So to do this substitution, we have to figure out what dy dx is. So we have to differentiate this with respect to x. Right? And remember, the multivariable chain rule says we have to do the derivative of the derivative of y holding u constant and treating x like the variable times dx dx plus the derivative of this formula that we're using for y with respect to u du dx. So taking the derivative of this with respect to x, we get just u times dx is 1, so u times 1, plus, Now the derivative of this formula with respect to u, that just leaves an x, times du dx. Okay, so now we can do our substitution. So we get dy dx, but right, we just worked that out. Dy dx is u plus x times du dx equals, and then on the right hand side, we can actually simplify this a little bit. This is going to be minus 1 minus y over x. So minus 1 minus y over x is, right, y is u times x, so that's over x. And now simplify this. Right, the x's are gone. Okay? So we succeeded in our substitution because all of the y's are gone and we're only left with u's and x's. Okay, but look, this equation is pretty nice because, well, it's separable. It also happens to be linear. The original equation happened to be linear, but this is a separable equation now. So if you actually work through this whole substitution process for a general homogeneous equation, it turns out that this substitution always makes the resulting equation separable. And we can solve separable equations. So to solve this, let's see. First we need to separate, so move the u to the right-hand side, so minus 1 minus u, and then separate, so we're going to divide this side by minus 1 minus u. Actually, let's leave the minus sign on the right-hand side. Divide this side by 1 plus u. Also, we're going to have to divide both sides by x and multiply both sides by dx. Right. Okay, so on the left, I made a bit of a mess of it, but it's du over 1 plus u. And on the right, we have minus 1 over x times dx. All right, and now that we have separated, we can integrate. On the left-hand side, we get natural log of 1 plus u. And on the right-hand side, we get minus natural log of x plus a constant. Don't forget your constant of integration. Now we need to find u, so exponentiate. We get 1 plus u equals, let's see, to simplify this, we're going to need to rewrite this as e to the minus natural log, actually, e to the natural log x to the minus 1 times e to the c, and let's rename e to the c capital A. So we get capital A times, right, e to the natural log x is just x to the minus first power. So then we can move the 1 over, we get u equals, this is a over x, minus 1. Okay, now remember, y was u times x. And we found u, but we need to find y. So now that we know what u is, we can just plug it into this equation to get y. So y is u, which is a over x minus 1 times x. So y is, distribute this x and simplify, it's a minus x. Okay, so we solved this homogeneous differential equation by using that substitution. Let's try another one. So this differential equation is really unfortunate looking. It's extremely nonlinear. It is first order, but it's extremely nonlinear because look, we have a y squared. So definitely we wouldn't be able to solve this using any other technique, but you know, maybe it's homogeneous. If you think about the idea of an equation being homogeneous, every term should have the same power of x and y. Right? In this term, it has just an x, so that's power 1. This term has just a y, so that's power 1. And this term Well, x and y are squared, but they're in a square root, and so that kind of counts as power 1. So maybe this is homogeneous. So to check if it's homogeneous, let's rearrange and see if it works. So let's see, we're going to have to move the y over and then divide by x. So we get dy dx equals square root of x squared plus y squared plus y over x. Okay, so this right-hand side here, right, the function that is the right-hand side of the equation, we've been calling that f of xy. So we need to plug in t times x and t times y and see if we get the same thing as f of x and y. So we get square root of tx squared plus ty squared plus ty over tx. Okay, now in this square root, right, we can, this part right here is t squared x squared, and this part right here is t squared y squared, and then we can pull the t's outside of the square root, so we get t times the square root of x squared plus y squared plus t times y all over t times x, and all the t's simplify away again. Now I've played a little fast and loose with my t because, you know, this should be absolute value of t, but really it's good enough for this equation to be true when t is positive. So this is a and you know, after we've simplified this is f of x comma y without the t's, and so this equation is a homogeneous equation. So since it's a homogeneous equation, we can try this substitution again. Y equals u times x. Again, we need to calculate what is dx dy using the chain rule in this multivariable formula. So it's partial y partial u du dx plus partial y partial x dx dx. I wrote them in the other order this time, not for any particular reason, it's just how it came out this time. Partial y partial u, that's just x times du dx plus partial y partial x using this formula is u times dx dx is 1. Okay, so that's dy dx. And now we can do the substitution. We could do the substitution in our rearranged version of the equation over here, but we can also do it with the original equation. It turns out it doesn't matter. So let me take our original differential equation, x times dy dx minus y equals the square root of x squared plus y squared. And now let's do our substitution. So as we do the substitution, remember, y's get replaced with u times x, and dy dx gets replaced with this whole mess. All right, so we get x times dy dx, which is x du dx plus u, minus y, and y is u times x, equals square root of x squared plus y, which is u times x squared. Okay. Now we should simplify this whole thing. So let's see, on the left-hand side we get x squared du dx plus, let's see, distributing the x over to there, we get u times x minus u times x, so those undo each other, nice, equals square root of x squared plus u squared x squared. Okay, now we can, inside the square root, we can factor out this x squared, it looks like. So square root of x squared times 1 plus u squared. To simplify this square root, let's add a condition that x has to be positive. So that means square root of x squared is x times the square root of 1 plus u squared. Okay, the left-hand side is now just x squared du dx. And now that we've simplified it, this equation is separable. Right? We can divide both sides by x squared. So du dx equals 1 over x times the square root of 1 plus u squared. While we're at it, we can move the dx over here, right? Multiply both sides by dx, and then divide both sides by the square root of 1 plus u squared. So du over square root 1 plus u squared equals dx over x. Okay, so we've separated. Now we can integrate. On the left are integrals with respect to u, and the antiderivative of 1 over square root of 1 plus u squared, you might not remember that one, but it turns out that it's arc hyperbolic sine, so it's inverse hyperbolic sine of u. And then on the right-hand side, that's natural log of x plus a constant, of course. Okay, and then to finish solving for u, just take hyperbolic sine of both sides. So hyperbolic sine of natural log of x plus a constant. Careful there. I almost put the constant outside hyperbolic sine, but it belongs inside hyperbolic sine. And then remember, we need to find y. Y is x times u, and so that's x times hyperbolic sine of natural log x plus a constant. Okay, so we were able to solve this differential equation even though it was extremely nonlinear and also pretty ugly in general.